Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to talk about derivatives of functions to functional powers. This is a continuation of logarithmic differentiation, or in other words, derivatives of logarithms. And this is probably the most crucial part of that conversation because this is where you get creative with your derivatives. So let's talk about this. The very first example is actually not exactly a derivative of a function to a functional power, but it showcases the idea of what you would like to do. You have the choice of taking the derivative of this as written, or in a very specialized way. Obviously that's pretty vague what I just said, but you could take the derivative as written. It's not a beautiful derivative, you could probably see. Let's go ahead and just showcase how you would go about this. You would say this is equal to this x squared plus 1, excuse me, over x squared minus 1, and this is raised to the 1/4 power. And then you would take the derivative of that, and that's going to be a chain rule, right? Y prime is equal to, I have some object to the 1/4 power. Let me just highlight that. That's the object to the 1/4 power. So its derivative will be 1/4 times that object to the negative 3/4 power, because you're losing 1 from the exponent. All right, then you have to rewrite that interior. It's an x squared plus 1, oops, divided by an x squared minus 1. Now that you've taken the derivative of the exterior, you have to hop inside to take the derivative of that interior, and that is a quotient rule. So then you go ahead and you take the derivative of the interior via the quotient rule, and you get this big old fraction that you attach as a chain here. The derivative of the numerator is 2x times the denominator, which is x squared minus 1, minus the numerator, x squared plus 1, times the derivative of the denominator, 2x, all over that denominator squared, and you are completely done taking that derivative. Of course, there's likely some cleanup you have to do here, and there actually is, and it's a bit of a mess. So, is there a better way to do that? Heck yes. If you know the output is positive, which it is because y is equal to the 4th root of something, and it's not going to be 0, then you could start by taking the logarithm of both sides. Now, why in the world would you want to start that problem by taking a logarithm of both sides? Well, let's see. You have the 1/4 power of x squared plus 1 over x squared minus 1. If I were to start this whole problem by saying, you know what? I know the output's going to be positive, so let me just go ahead and take the logarithm of both sides, natural log of the left-hand side and the natural log of the right-hand side. What this allows me to do is several things. One, I can use my algebra first to take this exponent all the way out in front of this logarithm. And I can also write, let me use the correct ink color for me. I can also write the resulting logarithm as a difference of logs. So natural log of x squared plus 1 minus the natural log of x squared minus 1. That is very advantageous because those derivatives are derivatives of these pieces much easier to work with. In fact, you can even multiply both sides by 4 if you wanted to. So we could do that. So I could say that's 4 natural log of y is equal to the natural log of x squared plus 1 minus natural log of x squared minus 1. Heck, even we could even start by raising both sides to the 4th power if we wanted to. There's nothing wrong with that, but actually I didn't do that, so we'll just continue the way I'm going. Now, if you take the derivative of both sides as written, so I'll take the derivative with respect to x of the left-hand side and the derivative with respect to x of this right-hand side, which I'm scooting over to make room for my derivative. If you do that, you'll see the left-hand side, well, that's 4. The derivative of natural log of something is 1 over that something times the derivative of the interior. And that's the derivative of the y with respect to x via the chain rule. And then on the other side, derivative of natural log of something is 1 over that something times the derivative of the argument, the something, minus the derivative again of the natural log of something is 1 over that something times the derivative of, again, that something. And this is much easier to deal with. You could just say dy dx now is equal to, well, you can see both those terms actually have a 2x in common, so I'll at least factor that out of there. I have 1 over x squared plus 1 minus 1 over x squared minus 1. And I'm going to divide both sides by 4 and multiply both sides by y. This will clean up quite a bit. Dy dx will equal x over 2. Finding the common denominator, which is x squared minus 1, x squared plus 1, it'll reduce down to the following. You could double check my mathematics on that, but that is absolutely correct. And finally, this value of y right here, we know what y is. We started by knowing what y was. Y is just the 4th root of x squared plus 1 over x squared minus 1. So that's what I'll trade that out for. That y that's in red up above will be traded out for the 4th root of x squared plus 1 over x squared minus 1. Now, technically, I suppose you could simplify this even further by canceling out those 2's and also taking out powers from the x squared plus 1's and x squared minus 1's, stuff like that. But that's really just a little bit of algebra in the back end. This is actually a very, very clean derivative, considering all the work that went into it. The full finalized answer would be x squared plus 1 to the 1/3, yeah, and times x squared minus 1 to the 5/4. And you could double check my laws of exponents there, and the negative sitting out front if you're wondering where that occurred or where that went. But that is the completely reduced derivative. The way we did it, again, handed a very complex function that would require the chain rule and a quotient rule. It could require product rules and stuff like that as well. We decided to take the logarithm of both sides to get that power out of there. Again, you could have started the entire problem just raising both sides to the 4th power. Had you done that, you would have y to the 4th is equal to x squared plus 1 over x squared minus 1. Again, at this point, you could totally take the natural log of both sides if you wanted to and break things apart, and you'd get down to the same answer we got. So this is a really great example of using natural logs or logarithms to simplify a derivative. I know you may think that that's not simple, but it actually is. It makes very complex computations much, much easier. We took something that involved a rational exponent, and then a chain rule, and then a quotient rule, and then a lot of simplification that we didn't bother doing, but we could have bothered doing. And we reduced it down to, using logarithms, just a chain rule. There was no product rule going on. And then some algebra at the end to simplify. All right, that's the entire problem. Now, let's see what I mean by derivatives of functions to functional powers, because this is actually a function to a constant power. This is the function x squared plus 1 over x squared minus 1 to the constant power of 1/4. But functions to functional powers, these are dangerous. These are what you have to pay attention in this lecture to. And that would be stuff like this. A function as a base, tangent of x, being raised to a power that's also a function. The power here is 1 over x. So it's a function, like an f of x, raised to a g of x power. That's a function to a functional power. When you're given something like that, the tactic is, one, maybe I should write in red what's bad. Here's what you should never do. Do not say, oh, y is f of x raised to the g of x, therefore y prime is take down the power and reduce the power by 1. That is terribly wrong. Wrong, wrong, wrong. That idea of bringing down the power and reducing the power by 1 only works when that exponent is a constant. That only works when it's a constant. So don't make that mistake. I see it all the time. Even though I say this, I still see it all the time. And it's basically 100% wrong. There's no partial credit that can be given if you do that. So what do you do? Well, in general, without me even inventing functions to work with, I could just tell you very easily what you could do. I'd like to get that g of x out of the exponent. Well, how do you unlock exponents? If you just said via logarithms, you're absolutely correct. You would take the logarithm of both sides. The natural log of the left-hand side should equal the natural log of the right-hand side. Now, there is a little bit of a hand waving here because I have not seen a textbook that mentions this, but you can't take the natural log of something that's 0 or negative. What you're taking the natural log of has to be positive. So that is a little bit of a hand waviness, and I think most authors avoid that conversation, and that's okay. That's fine. But if your instructor does make a big stink about that, then pay close attention to that, because it is actually very true. You can only do this if what you're taking the logarithm of is positive. And for now, I will just assume it is, even though it may not be. Let's just pretend as though it is. I'm going to take that exponent now, and I'm going to move it out in front of this logarithm. So I have the natural log of y is therefore equal to g of x times the natural log of f of x. And now I have a product of functions on the right-hand side, and one of them obviously is nested, has a function nested within it. Okay, fine. So I've got a chain rule when I take a derivative, but the reality is that's how I unlock that. So I can actually start working on this. And then I would just go ahead and take the derivative implicitly at that point with respect to x of both sides. So let's see this in action with this example. Y is equal to tangent of x raised to the 1 over x. Well, if y is equal to tangent of x raised to the 1 over x power, again, I'd like to unlock that exponent. I cannot just bring it down and subtract 1 from it. I have to actually take the natural log of both sides. So I'll say this implies, even though I don't know if this is actually going to be positive or negative, I'm going to assume that it is for this example. That implies the natural log of y is equal to natural log of tangent of x raised to the 1 over x, but we know that 1 over x can be brought out front. And now I could just take the derivative of both sides. It's actually a really nice way to do the problem. In this case, actually, I could even do this as a quotient rule on the right-hand side, and I think I will. So taking the derivative with respect to x on both sides. Well, the derivative of a natural log is 1 over its argument, and then you have to take the derivative of its argument. And then on the right-hand side, we have a quotient rule. So it's going to be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. So let's go ahead and write the denominator squared part because that's easy. The derivative of the numerator. So the derivative of a natural log is 1 over its argument. And then you have to take the derivative of its argument. And we're going to multiply that by the denominator. And then minus the numerator times the derivative of the denominator, which is actually just 1. And pretty much we're done. Not really. You have one extra move to do, 2 extra moves really to do here. Multiply both sides by this y to isolate dy dx. So I will put this in a big old bracket and I'll throw a y right there. And the stuff within the brackets, actually this whole fraction that you're looking at right here, I'm just going to multiply numerator and denominator by the tangent of x so that I don't have that silly tangent of 1 over tangent of x waiting out front. So I'll have a secant squared of x times x. I should write that x out front. Sorry about that. Move that over. So it's x secant squared of x minus, again, I'm multiplying both numerator and denominator by the tangent. So I'll have a tangent of x times the natural log of, again, I have to scoot things a little bit, natural log of the tangent of x. And this is all over, again, I'm multiplying top and bottom by tangent, so it's x squared times tangent of x. And again, I multiply both sides by y there, but what is y? Well, y is tangent of x to the 1 over x. So I'm going to go ahead and take that and plug that in right here. So I'll go ahead and plug in tangent of x raised to the 1 over x power. And that is completely done. There's nothing else you can do with that. So that's a really good demonstration of how to differentiate when you have a function raised to non-constant powers, basically a function raised to a functional power, or a variable raised to a variable power is another way to say that. Well, let's try this one last time. And I'm really truthfully mean one last time, because once you see it once, you've seen it a bunch of times. And notice how ugly this example is. These are the types of examples I like to make up because they're just kind of entertaining to me. I don't know why, because I'm a glutton for punishment maybe. So let's see how this works. I'll start by taking the natural log of both sides. So I have the natural log of y. The reason why, remember, is because I want to unlock this exponent. So the natural log of y will equal the natural log of, let me scoot this over because it's going to need that front, the natural log of the tangent inverse of x raised to that power, the ugly power that is being raised to. But I'm going to take that ugly power because we're taking the natural log and move it out front. And that ugly power is just a sine of x squared plus the sine of x squared. And that's it on that. And you can see this is going to be a terrible derivative. Honestly, it will be. But there's no other way you can do this. Now that you're to this point, it's going to be a product rule with some other stuff involved. So let's see, the derivative of the left-hand side. Well, the derivative of a natural log is 1 over its argument times the derivative of its argument. Now, product rule. I should have written this in different colors or something like that, but basically we have this first times this, let me use a different color, this last. So the derivative of the yellow function, derivative of sine is the cosine of its argument. But then you have to hop inside of its argument. Remember, we're dealing with the sine of x squared plus sine of x squared. So we've just taken the derivative of the sine. Now we're hopping inside and we're attaching to that derivative the derivative of this argument right here. So I'm going to use a parenthesis. The derivative of x squared is 2x. then plus, so I've already taken the derivative of that. The derivative of a sine is the cosine of its argument, so I've taken the derivative of that. But I have to attach the derivative of that x squared to that cosine because that's cosine was born of the sine of x squared. So the derivative of that x squared gets attached to that cosine. It doesn't get, so that's a big mistake that people will make. They'll attach that derivative to the outside of this. That's totally wrong. That derivative of x squared gets attached here because remember, it was the sine of, let me say it this way. It was x squared plus sine of x squared. Derivative of x squared is right here. The derivative of sine of x squared is all of this. That's the derivative of sine of x squared. So you don't want this 2x to be on the outside here. That's bad news. All right. So what we have just written down is the derivative of that yellow function. To that we'll attach the blue function, natural log of tangent inverse of x. Then we will hit the plus sign, write the yellow function, sine of x squared plus sine of x squared. And then we're going to take the derivative of the blue function. The derivative of a natural log is 1 over its argument. I'll just put the argument underneath this. So I've just taken the derivative of the natural log part. So let me erase that. And now I want to take the derivative of its argument, which is a tangent. Oh, and by the way, that was the square root. I'm sure people were yelling at me. I apologize. There should be square roots on those. I'll eventually see my mistakes. That's just how I am. There we go. All right. That makes it a little bit more challenging, actually. So the derivative of the tangent inverse, put the square root on here, is going to be 1 over 1 plus its argument squared, and its argument is the square root of x. So now I've just finished taking the derivative of the tangent inverse. Great. Times, because I have the derivative of a square root of x. Derivative of the square root of x is 1 over 2 times the square root of x. Or you could write it as 1/2 x and negative 1/2, your choice. Excuse me. And there's not much I'm going to do to clean this up, but I do have to multiply both sides by y. So here we go. Let's just do this. All right. So let's go ahead and say this implies, I'm just going to zoom in here, dy dx is equal to, and I'm going to multiply both sides by y. So I'm going to use a bracket here just so that I can contain the madness of this problem. And let's see, anything that can clean up. Technically, I suppose some people will say that you could factor a 2x out of both of these terms. Why not? Let's go ahead and do that. Factor out a 2x and we're left with a cosine of x squared plus sine of x squared. And then that is multiplying. We factored off a 2x, so that's 1 plus cosine of x squared times the natural log of the tan inverse of the square root of x. It's a bit of a mess, isn't it? And what else do we have? I'm just seeing if anything cleans up here. I think I'm gonna write this. Yeah, I'll just say plus. And I'm just gonna write it as a fraction. Sine of x squared plus sine of x squared. Oops, sine of x squared. All over, let's see, 2 root x tan inverse of the square root of x. And then times the quantity, 1 plus x, and that's 1 plus x because the square root is being squared. Let's see that we have everything cleaned up. And then we're multiplying both sides by y. However, I'm not going to rewrite this whole silly thing. Instead, I'll just grab this y here and erase my y there and say it's the group tangent inverse of the square root of x, and that block is being raised to the sine of x squared plus the sine of x squared. Man, that is a big bulky problem. You will not find something like this honestly in a textbook. But I highly recommend you go through the text and actually do as many of these as possible if you can. They can be really messy. This is the messiest you'll ever see, to be honest with you. This is not very typical. It's just one I made up. But it's good. If you could follow the mathematics there, then you're pretty solid. You could follow pretty much any of the mathematics that we're going to be doing in this course. Just remember, don't ever do this. If you have y is equal to a function to a functional power, do not write y prime as the function g of x times f of x to the g of x minus 1. That will get you kicked out of calculus. All right. That's all I'm going to say. You guys have a wonderful day. I'll see you next time.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.